In this lesson, we're going to be simplifying radical expressions, a little bit more difficult problems. So we'll be simplifying something like this that doesn't simplify as nice. So if we simplify cube root of x to the 20th. So a couple different ways to think of this. Let me do a little bit more of the mathematical way to do it. Is we're trying to find a perfect cube out of this, and we want to get the closest perfect cube that we can. So we're looking for groups of 3, and 20 doesn't break into groups of 3, but we can get close to that. We can get actually x to the 18th is a group of 3. So to do that, so we can actually cube root it, is 3 times what's going to get us our 18, and that's going to be 6. So we're going to break this apart into 2 pieces. One of them being a perfect cube, and basically whatever's left over. So this is 18, but we have 20 x's altogether. So we have 2 more x's that are left over. So this we cube root. Cubes and cube roots cancel each other. So that becomes x to the 6th. We can actually cube root it, so it comes out of the cube root. And this, we don't have enough x's. We only have 2 and we need 3. So that is going to stay on the inside. Now that's one way to think of it. There is potentially a lot faster way to think of it, but it may not work for everybody. Is before, if you had cube roots and you had a perfect number of them, so if you're looking for groups of 3, 18 is a perfect multiple of 3, you could just divide it. 18 divided by 3 would get you 6. But 20 doesn't divide by 3 evenly. So it's more like you got to divide it and see what your remainder is. So 3 goes into 20 6 times, so there's 6 groups that you can take out, and you're going to have 2 left over. So let's see that on another problem. We're going to take the square root this time of 24 x to the 10th, y to the 11th, and z to the 12th. All right. Now we're looking for perfect squares out of this, so we're going to see if we can do that division idea. So first thing I need to do is let's break 24 apart. And you can figure out what the perfect square is, but sometimes it's just nice to do a factor tree and see what 24 really consists of. So let's say you factor it into 2 and 12, and let's make our prime numbers stand out. 3 and 4, and 2 and 2. So 24 consists of 2 times 2 times 2 times 3. Those are the prime factors that make up 24. And if we're square rooting, we're looking for pairs. All right? That doesn't pair up. So this is what we're going to have left over on our square root. This we can actually square root. So if you put that together, that's 4, which would square root to 2. So 2 can come to the outside. And then the variables, we're going to do kind of the same thing. Well, you're looking for pairs. How many pairs can you get out of 10? You can get 5. So you can have an x to the 5th. How many pairs can you get out of 11? You can also get 5. However, you have leftovers. You have number leftovers and you have variable leftovers. So the numbers, these don't make a perfect square, so we'll just multiply them back together, and that'll be 6 on the inside. And then we were able to take out a perfect 5, but that left us with 1 left over. So we'd still have a y value on the inside. The z value we're looking to take into pairs, so this can become 6 pairs, and it would work out perfectly. No leftovers. That's it. So let's try the exact same problem, but we'll cube root everything rather than square root everything and see what the difference is. So still 24 x to the 10th, y to the 11th, and z to the 12th. So we already know that 24 is this, 2 times 2 times 2 times 3. But you're looking for cube roots. Now you're looking for 3 of a kind. Well, That's 3 of a kind right there. We can cube root that, so that can come out. We can't cube root that because there's not 3 3s, so that's going to stay on the inside. So for the x's, we're looking for groups of 3. So out of 10 x's, you can get 3 groups of 3 with 1 left over. And for the y values, you can also get 3 groups of 3. Right? So 3 times 3 is 9. You're going to have 2 left over. And for the z's, you're looking for groups of 3. You can get 4 groups of 3. And you don't have any leftovers. And don't forget that you're still cube rooting all of this that can't be cube rooted. So it has to stay inside the cube root. And that's it. That's simplifying a little bit more difficult radical expressions.